Long before USB, or even Ethernet, there was a simple idea: one wire to transmit and one to receive. That idea became UART. Today, we'll learn all about it and use it to communicate with a computer terminal. Welcome to the world of digital design. This is Metastable. So what is UART? UART is the Universal Asynchronous Receiver and Transmitter, and it's one of the simplest ways we can communicate between two digital devices. UART was originally a physical chip implementation, but now the term is used more broadly for the communication method itself. UART blocks have two lines: RX for receiving data and TX for transmitting data, which allows a block to act as both a receiver and transmitter. UART can be run in simplex mode, where the connection is one way, or duplex mode, where both blocks send and receive. To set up a UART connection, we cross-wire two blocks. One block's TX line goes to the other's RX, and vice versa. UART is called asynchronous because there is no shared clock between the receiving and transmitting sides. Both blocks have their own internal clocks for timing and synchronization, but there is no external connection. Without a shared clock, our receiver and transmitter must agree on a baud rate, or the number of symbols sent per second. Symbols are a topic for another day, but in this context, we can think of symbols simply as bits. This means our baud rate is effectively our bit rate, or bits per second. As long as our blocks agree, the baud rate can be whatever we want. Moving on to UART transmission, lines are serial, which means one bit is sent at a time. These lines are set high when not sending data. To start a transmission, we send a start bit by setting our line low. We then send our data bits from least to most significant. We can send anywhere from 5 to 9 data bits, with 8 being the most common number. After data, we can choose to send a parity bit, which is used for error detection on the receiving end. The line is then set high to signal a stop. This process can then be repeated to create larger and more complex messages. With a basic understanding, we'll build a UART module in VHDL. Now, there's a lot to cover with UART, so to get the most out of it, this will be a two-part video. In the first part, we'll build a transmitter, and in the second, a receiver. In our design, we'll implement a UART with a baud of 115.2, 8 data bits, no parity bit, and 1 stop bit. For our transmitter setup, we'll need 4 files: a debouncer, transmitter, top file, and constraint file. We'll start by importing the debouncer file we made in a previous video. If you don't already have the code, you can follow along with the debouncer video, or join my Patreon for free and get access to the entire VHDL tutorial code collection. Both links will be in the description. Next, we'll create the transmitter file. We'll start by adding two generics: our clock frequency and the baud rate. Our basis 3 clock runs at 100 MHz, and our baud is 115.2. After that, we'll add our ports: clock, reset, DIN or data in, the enable strobe for data in, busy to let the system know we're sending data, and the TX line itself. In the past, we've used enable signals to show data is ready, but enable can mean different things for different systems, so to be more specific, we'll use the term enable strobe. This indicates that the data connected to the enable is only valid for a single clock cycle. Next, we'll add a constant clocks per bit. To achieve the correct baud rate with a faster system clock, each bit must be held for multiple clock cycles. Clocks per bit is the number of clock cycles each bit should be active. It's calculated by taking the clock rate over the baud. So with a clock rate of 100 MHz and a baud of 115.2, our clocks per bit comes out to 868. Our result is actually not quite a whole number, but since it's an integer, it'll automatically truncate any digits after the decimal point. From here, we'll create a new state machine type. This type will have 4 states: idle, our default, start to begin a transaction, data to send our data bits, and a stop state to end the transaction. Then we'll create a signal for our new state machine type, TX state. We'll also add a message signal to hold on to the data input received. Additionally, we'll add a counter to hold each bit for 868 cycles, and an index to keep track of which message bit we're sending. Now we'll create a process. We'll create reset conditions, notably with TX being set to 1. Then we'll implement the state machine. During idle, TX is set high, and we wait for a data enable strobe. Once received, we assign our message to data in, let the system know we're busy, and move to the start state. In the start state, we set TX to 0 and wait clocks per bit, or 868 clock cycles, and then reset our counter and move to the data state. In data, we set the TX to our message bits, starting with the least significant bit. Then we wait clocks per bit, after which we'll send the next bit and do this until we've sent our entire byte of data. We'll then move to the stop state, where we set TX high and wait another 868 clocks before returning to the idle state. With a complete transmitter, we'll move on to the top file. Our ports are clock, reset, button, RX, and TX. In the architecture, we'll first create the message that we want to send to the terminal. Let's start with something simple, like a single character to verify a connection with our terminal. Let's send an exclamation mark. We can represent an exclamation mark in binary with this value. In addition to representing unsigned values, binary can represent ASCII characters. ASCII stands for American Standard Code for Information Interchange, and it's the foundational system used for representing text on computers. You can easily find the reference for all ASCII characters online. Next, we'll add TB strobe, busy, and data, followed by our button signals, button DB, strobe, and previous. TB strobe and data will be used in the future, but won't be used for this specific test. We'll then move to the design logic and add our debouncer and an edge detect process for the previous debounced value. Then we'll assign button strobe. From here, we'll add our transmitter. We'll assign the TX message constant to the data in and the button enable strobe to the transmitter's input strobe. We'll then copy down a new constraint file and uncomment the clock, button C and R for button and reset, and uncomment and rename the TX and RX lines. We'll then build the UART in Vivado. Normally, this would be where we could test the design on hardware, but we first need to set up a computer terminal connection. With the Basis 3 plugged into our computer, we'll check the device manager. Under ports, you should see a USB serial port. This USB connection is actually how we'll be sending and receiving data over UART. In order to connect over UART, we first need to identify which COM port represents our Basis 3. For me, it shows up as COM4. From here, we can open a terminal. To communicate with a Windows computer or a Linux machine, we'll download a program called PuTTY. Once downloaded, we'll be greeted by the configuration screen. We'll move to the Serial tab and put in our COM port, baud rate, and bit options and set flow control to none. I would highly recommend saving this session as it'll make future use much easier. From here, we can click Open to start a connection. Alternatively, on Linux, you can just open up a new terminal and run sudo apt install screen, or your distribution's equivalent, if you don't have screen installed, and then run this to see which USB devices are connected. I found the easiest way to confirm your USB device is to run the previous command with the device both plugged in and unplugged to see what changes. We'll then run this command, which creates a UART connection based on the given device and baud rate. Now we can verify our design. When we press the center button, we see an exclamation point on the screen, which means our design is working. With communication established, let's try sending an actual message. Let's send a friendly hello. It might not seem like it, but this will actually require a lot more work. A string of characters requires a controller that can change the data once previous data has been sent. We'll add this functionality to UART_control.vhd. We'll have the ports clock, reset, button strobe, TX busy, out, and strobe. The TX ports will allow us to communicate with and send data to the transmitter. Now in the architecture, we'll define our message. For the string hello, we'll create a constant message ASCII type standard logic vector from 55 down to 0 and set it to this. Let's break down how this equals hello. First off, we're using a format called hexadecimal, which is base 16, which means there are 16 values per digit from 0 to 9, continuing with A as 10, up to F for 15. We can use it to make long binary values more understandable. 4 binary digits can be represented with just one hexadecimal digit. This allows us to use 14 digits instead of 56 ones and zeros. We'll also create a constant message max to help us index the ASCII message. we'll need a pointer to shift which part of the message we're sending to the transmitter, an internal busy signal to detect the rising edge of TX busy, and a continue signal to let the controller know we still have more data to send. We'll then create the controller state machine, which will have 3 states: idle, shift, and busy. In idle, we wait for a button press and move to shift if detected. In shift, we decrease the pointer so that the next character is ready for the transmitter. In busy, we wait until the transmitter is done and then return to idle. We'll create a signal for this new type and then create a process. Inside, we'll reset our signals and outputs to their initial values. Outside of reset, our internal busy is assigned to TX busy, and our output strobe is assigned low. From here, we'll implement our state machine. If we have a button press strobe or a continue, we assign the current data byte to TX out and set our TX strobe high and move to shift. In shift, if our pointer is greater than 0, we subtract 8 for the 8 bits we just sent. Otherwise, we move back to our max value. The reason we decrease our pointer each time is because our message uses down to notation, meaning the first character H is bits 55 down to 48. So to get E, we need to access message ASCII from bits 47 down to 40, which is 8 bits down from H. We then move to the busy state. Here, we check that our transmitter was busy last cycle but isn't currently. If we have unsent bits in our message, we set TX continue high. Otherwise, we set it low and move back to idle. And that's all for the controller. Now we'll implement our controller in the top file and wire it to the transmitter. We can then retest our design in a new terminal. When we press the center button, we get a hello in the terminal. The cool thing about this is we can now send any kind of message as long as we know the ASCII hex and put in the correct bounds. But with that, you have a working transmitter. That's all for this video. In the next one, we'll build a UART receiver and have some more fun with our transmitter. Leave a like if you enjoyed the video and subscribe to stay up to date. See you in the next one.